is part A of the Kinetics lab. I want to show you how to do some of these calculations. We'll start off with the molarities, and the molarities that I'm talking about are the ones that go down in this region right here. So where I've put those arrows. So let's start off with the first one here. We're looking at the concentration of acetone. I'm going to put a 1 here, and the 1 here is for the reaction mixture that I'm pointing at over here. So that's the first one that we're dealing with here, and that would be 4.0 molar is the concentration. And what we need to do is figure out what it would be once we diluted it into the total volume of the solution. Now if you look at the total volume, it's going to be 10 plus 10 plus 10 plus 20. That's 50.0 mils. Now you might be wondering why I don't convert these guys into litres. That's because the mils will cancel. I'll still be left with molar at the end, or molarity. And the molarity here would be 0.80 mils once molarity once I take significant figures into account. So that's 4.0, which is 2 sig figs. That's 2 sig figs over here as well. So that's how I know that this is going to be 0.80. And now incidentally, when you look at these volumes here, you can see that's 10, and that's 10. So you know that those are all going to be the same. And since that's 20, you know that this one down here is going to be double. So that would be 1.6 molar down there. And I know that automatically. I don't have to do any math on that. Now I do the same thing over here for the molarity of HCl, and just follow the same pattern here. It'd be 0.20, and the molarity of the iodine would be 0.0010. Now we're also going to have to get some times here. I'm going to pick up a couple of times, then I'm just going to put them up the top here. These are just going to be just random times that I've made up myself, not necessarily what you're going to find, but they're in seconds as well. And I'm going to put some temperatures in here as well, so say 22 and 20. We'll say 22.0 and 20.0 degrees Celsius. And then on the second trial, I'll do, say, 110, and I'll do the same temperature. And I will do the same temperature as that as well. So once I've done that, I can then go ahead and get the rates of these reactions. So this would be 1.6, this will be 0.20 because it's the same volume, this would be 0.0010 because that's the same volume as well. So you can see the only difference here is going to be between the acetone in 1 and 2. Let's look at the average reaction time. The average reaction time for the top one, you can see it's 210 and 190. I'm hoping you can see it would be 200 seconds. And on the other ones, 110 and 90, that would be 100 seconds. So now we can look over here at the rates of the reactions, how we get that. Now the rate, and this would be for mixture 1, is going to be the concentration, or we'll say the change in concentration of I2, 1 over the time. See, what's happening during this reaction is that it's turning from a yellow color to a colorless color. The yellow color is actually the iodine. You'll notice also that the iodine is very low concentration relative to the other things that are in the reaction mixture. So you can see that that's going to end up being the limiting reagent. It's going to end up being used first. So when the yellow color disappears, it becomes colorless. We know the iodine is gone. And that would represent then the change in the concentration of iodine, which is going to be 0.0010, which is what it starts at. And it goes down to 0 eventually, of course. But that's going to be the change in concentration of iodine. And the time there, this is for the first one, is going to be 200 seconds. And that comes out to be about 5.0 times 10 to the negative 6 and that's molar per second as the unit on the rate there. Now we do the same thing with rate 2, and that comes out to be 1.0 times 10 to the negative 5 molar per second. Applying the same formula to that. So I'm going to go ahead and put those results in here. So 5.0 times 10 to the negative 6 and 1.0 times 10 to the negative 5. So that's how I'm going to get the rates, and now I need to get the orders. I'm going to get the order with respect to acetone first. And the way I do that is to compare rate 1 and rate 2. Now if you look closely at the concentrations here, we've got 0.8 and 1.6. We've got 0.2 and 0.2, 0.0010 and 0.0010. So you can see that all these concentrations, both of these are going to be the same, and this one is the one that's different, the molarity of the acetone. That allows us to determine the order with respect to the acetone. So remember what the rate law looks like. It's rate equals K acetone, and that's to a certain power M, HCl, and that's to a certain power N, and the I2, which is to a certain power P. Now this may be expressed as H plus as well. You might see that because that's actually what's going to be doing the work here, not HCl necessarily by itself. But you might see H plus there instead of HCl. And what we're interested in here is these values M, N, and P. And you can see that if these concentrations are the same, the HCl and the I2, then those are going to end up cancelling, and all we'll be left with is what's going on with the acetone. So here's how we do that. We'll do rate 2 over rate 1 equals, and it's going to be the acetone to the M, and that's going to be 2, and over acetone 1 to the M down here. Then we've got the HCl 2 to the N, HCl 1 to the N, I2 to the P, and that's 2, I2 1 to the P. Now these are going to be the same for the HCl and the I2, so you can see that those are going to end up cancelling. That's going to cancel. The K's here, of course, will cancel too. So what we're left with is what we've got over here. So I'm going to go ahead and substitute those in, and you'll see why we did rate 2 over rate 1 in a second rather than rate 1 over rate 2. Let me make that a little bit straighter. There we go. So we've got 1.0 times 10 to the negative 5 over 5.0 times 10 to the negative 6. You can see that the top one now is bigger than the bottom one, which makes it a little bit easier. And then we've got 1.6 over 0.80. Now it's 1.6 molar to the power of M, and we've got 0.80 molar to the power M as well. So you can see here that once we do the math here, this ends up being 2, or 2.0, and that ends up being 2 to the M, and you can see that M would then be 1. Now M is always going to be rounded, so let's say this wasn't exactly 2.0, let's say it was 1.8, and let's say you had to solve for 1.8 equals 2 to the M. How would you do that? Well, what you could do is you could use this logic here, and that is if you've got something where x equals y to the z, and you wanted to solve for z, then z would equal log x over log y. So that's how you can solve it, by using log logic. in this case, m would equal log 1.8 over log 2, if you want to do it that way. But here you do the same thing. You'll end up clearly with a value of m equals 1 over here. Now we're going to do something similar with the HCl and the I2. I think you can handle that now. And if you look closely at the data here for the HCl, you can see that we have 10, 10, 10, and 10 on the top one, and then on the third one we've got 10, 20, and 10. So the difference there is in the HCl. So if we compare rate 3 over rate 1, we'll be able to get the order with respect to HCl. And for I2, you can see we got 10, 10, and 5, 10, 10, 10, and 5 up here, and we would do rate 4 over rate 1 for the iodine. Right, that's for the iodine, that's for the HCl. And that will allow us to pick up the reaction orders that we want to pick up. I'm going to go ahead and delete a bunch of this stuff that we have here so that I can show you how to do the rate constant. So just bear with me for a second while I get rid of some of this other stuff here. Okay. So when we're looking at solving for the value of K, we're interested in using the rate law, and the rate law looks like this. Rate equals K, acetone to the M, HCl to the N, and I2 to the power of P. And what we're interested in doing here is solving for K. Now what I'm going to do is I'm just going to do this for reaction mixture 1, which is this data, this data over here, just all of that. Now we do have some information here. We do have the rate, which is 5.0 times 10 to the negative 6 molar per second, which I picked up off here, right? Next I've got my K, and I've got K acetone, which is going to be 0.80 molar. I've got an M value of 1, and for HCl I've got 0.20, and I've actually made up a value for that. I'm going to say it's 3, but you might find it to be something different. In fact, I'm going to say that you will probably find it to be something different. Hang on, let me put a unit in there as well. That's going to be important. Molar, make that cubed. And then 0.0010 molar, and I'm going to make that squared. So these are the values of M, N, and P, and N and P are actually made up. N and P are not real. Okay, so I'm just pointing that out, okay? I wanted just to be able to show you how to do this without giving away how to do it. Alright, that's my point here. So now what I can do is I can actually solve for this value of K. So K is going to equal 5.0 times 10 to the negative 6 molar per second. That's going to be divided by everything that I have here, 0.80 molar times 0.20 molar, and that's to the 3, and 0.0010 molar, and that's to the power of 2. Now if I do the math on that, here's what I end up with. 5.0 times 10 to the negative 6 molar per second over, and it looks like 6.4 times 10 to the negative 9. So that's the numerical value once I put all that into my calculator. So it's 0.80 times 0.20 cubed times 0.0010 squared. But the other part of that unit is the molar. We've got molar to the 1, molar to the 3, molar to the 2. And when we multiply all of those together, we get molar to the 6th. Now the way I get the 6th there is that's going to be 1 plus 3 plus 2 is 6. Because whenever you're multiplying powers together, you add the powers. Alright, so anything with powers, it's like if you've got a to the x times a to the y, that equals a to the x plus y. So that's what I've done there. So that's m to the 6th. Now once I solve for that, I end up getting 780, and the unit there would be m to the negative 5 s to the negative 1. Now the s to the negative 1 is because per seconds is the same as s to the negative 1. And the way that I get the m to the negative 5, I get that by going m to the 1 divided by m to the 6th is equal to m to the 1 minus 6. So it's very similar to what we're doing over here, except with division, it's going to be subtraction and not addition. So that's how I end up with m to the negative 5 s to the negative 1 as my unit for k.